In this video, we're going to look at the derivatives of parametric equations. As a quick review, a parametric equation is parametric equations are just multiple equations, for instance, x of t equals and y of t equals, that are all related through the same parameter. In this case, the parameter or parametric variable is t. And the first derivative is actually pretty easy. So if I want to find dy dx, the slope of the parametric curve, that's just going to be dy dt divided by dx dt. The biggest possible pitfall here that happens to me, happens to many people, is parametric equations are generally written x of t equals y of t equals. Make sure you put dy dt on top. The second derivative is a little bit more difficult, so d squared y dx squared. It is going to be the derivative with respect to t of the first derivative, all divided by dx dt. It is definitely worth noting and remembering this is not the same thing as the second derivative of y with respect to t divided by the second derivative of x with respect to t. So this is what most people might think right off the bat. The problem is the second derivative is the derivative of the first derivative, so this makes sense in the numerator. But I don't know if my x function is moving forward or backward, so I need to keep in mind, or it could actually be stopped. I could have dx dt be 0. So I need to keep in mind what's going on down here. So don't fall into that trap. You need to actually go through this process. It's a little bit trickier. Let's see a couple examples of how this works. So the first one, find the equation of the line tangent to this at t equals pi over 3. Well, to find the tangent line, I need the point. So let me find the point first. So I need to find x of pi over 3, which will be the cosine of 5 pi over 3. Cosine of 5 pi over 3 is going to equal 1/2. And I need to find y of pi over 3, which is going to be the sine of 4 pi over 3, which is negative root 3 over 2. And so my point is the point 1/2 negative root 3 over 2. After I have the point, I need to find the slope. So I need dy dx. I take the derivative of sine with respect to t, so that's going to be 4 cosine 4t. Doing chain rule, derivative of sine is cosine, derivative of 4t is the 4. And divide that by the derivative of x of t, which is here. So the derivative of cosine is negative sine. And the derivative of 5t is 5, a little bit of chain rule there. And I need to evaluate this at pi over 3, so dy dx, evaluated where t is equal to pi over 3, is going to equal 4 cosine of 4 pi over 3, divided by, I guess I'll bring the negative out front, 5 sine of 5 pi over 3. And the cosine of 4 pi over 3, I'll bring it down here, so I have negative 4. The cosine of 4 pi over 3 is going to be negative 1/2, divided by 5, and the sine of 5 pi over 3 is going to be negative root 3 over 2. And working these halves through, I get negative 4 over 5 root 3. And if you don't rationalize the denominator, that's fine. And I can get to my answer. So I get y equals negative 4 over 5 root 3, x minus 1/2 minus root 3 over 2. If I want to, I could rationalize the denominator by multiplying numerator and denominator by root 3 and get negative 4 root 3 over 15. Neither one really makes a difference. They're not making such a big deal on the AP test about rationalized denominators. Okay, let's graphically see what the heck just happened. So here is our parametric function. X of t equals cosine 5t, sine of t, or sorry, y of t equals sine 4t. In here, when I put in the point, I get this point right here at 1/2 negative root 3 over 2. And when I go ahead and do that tangent line, so you can see, okay, yeah, it looks like it's decreasing. And when I put in that tangent line, I get this. So, as you can see clearly, it looks pretty good. All right. Next example. Given the parametric equations x of t equals 2t squared minus 3 and y of t equals t squared minus 4t plus 3, is 5, negative 1 a relative minimum, relative maximum, or neither, and justify your answer. So in here, in order to be a relative minimum or relative maximum, we need to see that dy dx must equal 0. Or it could be undefined, okay? I need a critical point, though. And if dy dx is 0, and the second derivative is greater than 0, meaning concave up, we'll get a minimum. If the second derivative is less than 0, meaning concave down, I'll get a maximum. So let's go through the process. First thing I should look at is I need to get a t value. So they gave me 5, negative 1, but I need a t. So here's how I do that. Well, x is 5, so I can set up the equation 5 equals 2t squared minus 3 and solve for t. So I'll add 3 and get 8 equals 2t squared. Divide by 2, 4 equals t squared. Take the square root, and I get t is plus or minus 2. But that actually doesn't work in all cases. Both positive and negative 2 aren't right here, and here's the thing. So I got this from x, but let me see what happens if I do the y equation. So I'll do negative 1 equals t squared minus 4t plus 3. And this is quadratic, so I'll add 1 to both sides and get 0 is equal to t squared minus 4t plus 4, which means 0 equals, this is a perfect square trinomial, t minus 2 squared. And so t can only equal positive 2. So negative 2 is not one of our t values. So t is 2. Now that I have t, I can take the derivative and make sure that the derivative is equal to 0 or undefined. I need a critical point. So dy dx will equal, the derivative of y with respect to t is 2t minus 4. The derivative of x with respect to t is 4t. And evaluate this at t equals 2 will give me 2 times 2 minus 4 over 4 times 2, which is 0. So that's good. Now I need the second derivative. And so in order to get that, the second derivative, I need to take the derivative of the first derivative, which was this. So 2t minus 4 over 4t, which is going to involve some quotient rule, and divide all of that by the derivative of x with respect to t. So I'll write dx dt here. It's pretty easy. I'm going to put it in a second. So quotient rule here. So I have v times the derivative of u. So I have 4t times the derivative of the top, which is 2, minus u times the derivative of v, so 2t minus 4 times 4, all over v squared, 4t squared, all over dx dt, which is going to be the derivative of this, which is 4t. Okay, cleaning this up a little bit, I'm going to do it right here, I'm running out of room, so I get 8t here, I get minus 8t plus 16 here, so 8t's cancel, I have a positive 16, and these I can combine to get 4t cubed, so I get 16 divided by 4t cubed, which is 4 over t cubed, and evaluate that when t is 2, well, that's going to be 4/8, which is 1/2, or more importantly, it is greater than 0, which means, not that, we have a minimum. Justification, because the first derivative is 0, second derivative is positive. Let's take a look and see graphically what's happening. So let me turn off this graph stuff. Let me zoom out, because this is going to be a larger thing. And here's my parametric function. Okay, looks like a tilted parabola because it is. The point we're looking at is 5, negative 1. And you can clearly see now, yeah, all right, that's a minimum. It's the lowest point on this curve. It's not the vertex because the parabola is tilted, but it is a minimum. Okay, one final example. Given this parametric equation, find all coordinates of the intersections of all horizontal and vertical tangents to the curve. And so basically, horizontal tangents means that dy dx equals 0. Vertical tangents means dy dx is undefined. And the trick to it is, if dy dx is 0, that means that the numerator had to equal 0. And in most cases, if dy dx is undefined, that meant that the denominator had to equal 0. Now, of course, there are exceptions. Where I guess I could have dx approaching infinity, so this will approach 0. Or I could have a 0 over 0 case, which is a special case. I'm going to avoid those here, but know that there are exceptions. If you desperately want to see some examples, comment below. I can put up a video where we do get some of these cases with 0 over 0 to see what happens. But let's go through and do this process. So we know that dy dx is the derivative of y with respect to t, which is just going to be 5 cosine t, and over the derivative of x with respect to t, which is going to be negative 2 sine of t. Okay, to get the horizontal horizontal tangents, I'm going to set the numerator equal to 0. That will make this quotient 0, so long as I don't have 0 over 0. So 5 cosine of t equals 0 means that cosine of t is equal to 0. That happens at t equals pi over 2 and 3 pi over 2. Now, because both of these are periodic with a period of 2 pi, I've gotten every t from 0 to 2 pi. I've covered everything. All right, now let's look at the vertical tangents. So vertical, we will set the denominator equal to 0. That will make this undefined. So negative 2 sine of t equals 0. Divide both sides by negative 2. You get sine of t equals 0. Sine of t equals 0 at t equals 0, pi, and I'm going to put in 2 pi, but that's coterminal to 0, so I won't actually end up using both. And here's the last kicker to it. These are not the coordinates. These are the t values. So to get the coordinates, I had to put pi over 2 into this and put 3 pi over 2 into this. So when I put pi over 2, cosine of pi over 2 is 0, times 2 is 0, plus 3 is 3. And sine of pi over 2 is 1, times 5 is 5, minus 1 is 4. So that gave me the point 3, 4. Same thing here. When I put 3 pi over 2 in, the cosine of 3 pi over 2 is 0, times 2 is 0, plus 3 is 3. The sine of 3 pi over 2 is negative 1, times 5 is negative 5, minus 1 is negative 6. And for these, I'll do the same thing. So I'll put them in. So I get something for 0, something for pi, and 2 pi is going to give me the same thing as 0. So put in 0, cosine of 0 is 1, times 2 is 2, plus 3 is 5. Sine of 0 is 0, times 5 is 0, minus 1 is negative 1. When I put in pi, cosine of pi is negative 1, times 2 is negative 2, plus 3 is 1. Sine of pi is 0, times 5 is 0, minus 1 is negative 1. And if I put in 2 pi, you'll see cosine of 2 pi is 1, times 2 is 2, plus 3 is 5. It's going to be the same as this. Sine of 2 pi is 0, times 5 is 0, minus 1. Okay, so these here are the 4 intersections. These are where the horizontal asymptotes, or horizontal tangents intersect. These are where the vertical tangents intersect. And let's take a look and see what's going on here. So I'm going to turn off these, turn on our new graph, and we can see, all right, I have a vertical tangent here, a horizontal tangent here, vertical tangent here, horizontal tangent there. Let me turn those on. So vertical tangent, horizontal tangent, horizontal tangent. And those coordinates, we have this at 5, negative 1. We have this one at 1, negative 1. We have this at 3, 4. And we have this one at 3, negative 6. So you can see analytically we did all this work, and it completely meshes with graphically what's going on. All right, I hope that helped out. Feel free to comment below with any questions, or if you'd like to see more on what's going on here and some of the special cases where I would get to 0 over 0. And I'll get back to some more of this parametric, polar, and vector stuff in the next couple of days.